Okay, welcome to Chapter 7. This is Intro to Sampling Distribution, so notice the word sampling. We haven't been talking about samples in a while, so you have to review all the terminology from back in Chapter 3. So I took some pictures of the textbook. If you don't have it with you, you're going to need to write down these vocab terms. So a statistical inference is what we're going to start doing in Chapter 7, which is just estimating and drawing conclusions about a population based on information contained in a sample of that population. So you need to write that down as part of your notes. I'm not going to have you write down the terms statistics and parameters, but you do need to review those. So it's a characteristic of a sample is a statistic, and a characteristic of a population is called a parameter. We're going to see what those look like here in a second. And then you do need to write this down. For sampling error, it's the distance between the point estimate and its target parameter. So review what a point estimate is, and then we're going to see what each one of these things look like. So characteristics that we have discussed so far include the mean, the standard deviation, and a proportion. So these are three characteristics we've talked about. If we're talking about a characteristic of a sample, it's called a sample statistic. And the mean of a sample looked like x bar. The standard deviation of a sample was the lowercase s. And a proportion was a p hat. Remember, that was an estimated proportion. For a population, the mean is mu. The standard deviation is sigma, and the proportion of a population is just p. So if we want the sampling error, how far off between the point estimate and its target parameter, we take the absolute value, that means we're not going to have any negatives, of the difference between these two parameters, so the sample statistic and the population parameter. So x bar minus mu, s minus sigma, and p hat minus p. That is how we find the sampling error of either the mean, the standard deviation, or the proportion. Let's consider this whole thing a population. And I'm going to learn about the population by taking samples from this population. So if I want to take the population mean, remember that is the sum of all the x's over the sum of how many there are. So I have Amber for 10, Brandon, Chantal, and Dave, and Emma. And there are 5 of them. So if I do that, takes them an average, mean, estimated time, remember those are all the same term, of 16 minutes. Now, if I want to take a sample, I can find a sample mean, but I have to decide who am I going to choose. So if I happen to choose Amber, Brandon, and Chantal, then I'm going to have still sum of x's, but remember it's lowercase n because now I only have 3 in my sample size. And I have 10 plus 20 plus 5. So my average there comes out to 11.67 minutes. So even though the population, for all of them, the average time was 16 minutes, for this one sample, I'm just going to give this a little 1, it takes them about 12 minutes. Now, the reason I gave it a 1 here is because I can take a different sample with 3 different people and get a different number. using the same equation, but choosing different people to be in my sample. So if I chose Amber, Brandon, and Dave instead of Chantal, then I'm going to have 10 plus 20 plus 30 with a sample size of 3 still, right? And I would get an average of 20 minutes. And that is different from the first sample, also different from the population. Okay, so what we're going to see is that we can take so many different combinations just within these 5 people and get different averages, different means. So we're going to take that and make a distribution out of them. That is what our sampling distribution is. It's just a display of where we should expect things to be. So where we've seen this term before, distribution, is in a normal distribution. We won't always have that, but we have some certain facts that will allow us to talk about sampling distribution. So let's look at what those are. Fact 1 is that the mean of the sampling distribution of the sample mean x bar, so this is for samples, will actually always be equal to the population mean. So this symbol here, mean of the sample distribution, that's what that symbol represents. And this symbol is just the mean of the population. So what is that saying? Let's go back to this example. That's saying, I'm going to draw this here as a number line. Let's say for my first sample I got 11 point, here's 30 minutes, 11.67. So this is my x1. And then when I did x2, I had an average over here somewhere. But the population mean was 16. So I'm going to get so many different x1, x2 averages for the samples, but overall, this will always be true. This is a fact about it. No matter what, if I averaged all of the different sample means that I get, I will always end up getting the population mean. Okay, if you want to see an example of that and actually go through and calculate each one, you can do that. Or I can show you really quick in the book. This is what they end up looking like. So these are all individual samples, sample means, which are x bars. But if you added these dots up and divided by however many there are, you would end up with exactly the population mean. So you can test it every time, or you can use the fact 1 and say that I know the mean of the population is always going to be the mean of my sampling distribution. Fact 2 talks about the standard deviation. So the standard deviation of the sampling distribution, we represent that as sigma with a little x bar on the bottom, because remember, we're talking about samples. Now, this is not directly equal to the population standard deviation. It is the population standard deviation divided by the square root of the sample size. That's a lowercase n. So you will have to be doing calculations for that one. For fact 3, it's literally just a fact, no equations. So it's saying that if I have a sampling distribution for a normal population, remember normal means that it is bell-shaped, then it's normal regardless of the sample size. So if my population, so let's say the population is normally distributed, then my sample will also be normally distributed. Which makes sense because if you're taking the sample from the population, then it should be just little pieces from it, little facts, little x's. Okay. Fact 4 is just a notation. So I'm not going to require you to use this or to be able to write it as that. But if it comes up in the book or in one of the word problems, I want you to be able to know that if it says normal with a parentheses and a comma, the first number in there is the population mean. The second number in there is the standard deviation of the sampling distribution. Okay. And then fact 5 is that we can standardize just like we did before. Now, the symbols look slightly different just because of these little X bars, but remember, this from fact 1 told us that it's just exactly equal to the population mean. And this one from fact 2 is equal to the population standard deviation divided by the square root of n. So you're going to be given problems that give you these pieces, and you have to know how to plug them in to be able to standardize. And I am going to do an example problem with that. Okay, let's look at this example here. If you're following along in the book, this is example 7.6. So suppose that statistics quiz scores for a certain instructor are normally distributed. As soon as you see that, underline it, normally distributed, with a mean of 70 and a standard deviation of 10. Find the probability that a randomly chosen student score will be above 80. Now, these are problems that we did in chapter 6. So we're going to be building off of chapter 6 in chapter 7. So find the probability that a randomly chosen student score will be above 80. What it's asking me to find is the area under the curve above a score of 80. They told us that the mean is 70 and my standard deviation is 10. So if my standard deviation is 10, then that's one standard deviation over. So if you have your empirical rule memorized, then you know that this is the same thing as the mean being 0. Above the 80 is actually just above 1. So the probability of having an x greater than 80 is about 0.1587. This is the same thing. So these are the x's. This is the z-scores. This is the same thing as the probability of the z being greater than 1. They're just on two different distributions. One of them is your normal, your values of x, and this one is your values of z-scores. So remember, this is the standard normal, where your mean is 0 and your deviation is 1, and this is just a regular normal curve. Now, if I wanted to find the mean of the sample, or the standard deviation of the sample, what might I do? This is for part B. So suppose that over the years the instructor has had many sections of size n equals 25. What kind of distribution is the sampling distribution of the sample mean? What kind of distribution? So earlier it told us we had a normally distributed population. So if we have a population that's normal, and then he takes sample sizes of 25, by fact, I think it's 3, tells us that if the population is normally distributed, then the sampling distribution is also normal, or normally distributed. Okay, if I wanted to find the mean of that normally distributed sampling distribution, then I would just need to look at the mean of the population. That's fact 1, which in this case happens to be 70. If I wanted to find the standard deviation of the sampling distribution, I would need the standard deviation of the population, which they told us to be 10, and I need the square root of the sample size, which in this case is 25. So square root of 25 is 5. So for our sampling distribution, the mean is 70 and the standard deviation is 2. Why would I need to find those if it doesn't ask me to find them in the question? Well, you will need those in something like this question. Find the probability that a sample of 25 quiz scores will have a mean score greater than 80. They want to know the area under the curve with a mean score greater than 80. But now I have a mean of 70 and a standard deviation of 2, so be very careful. What I'm going to do is standardize using my formula and plug in what I know. So these are all sample pieces. Remember, this is x bar is sample mean. This here we calculated to be 70, which was just because the population had it 70. And then the standard deviation of my sample is 2, because we calculated that up here. So what we're looking for, what the question is asking, is what is the probability of getting a mean that is greater than 80? So now that we have all our numbers in place, we can plug this in here. You get 80 minus 70 divided by 2 is 5. So this is the same thing as asking what is the probability of my z-score being greater than 5. You can use your calculator to do that, and when you plug it in, you get 0.000000287, which is about 0. There's a 0% chance, 0 probability that you will have an average mean score greater than 80. Now, it doesn't say that you're going to find 1. That's not the probability of finding 1. It's finding the average, the mean of one of them being greater than 80. So we can go on and use this with percentile as well. So this time, 95th percentile is this area under the curve being 0.95. And so I'm looking for this number here. I don't know what goes there. What is the x bar that represents that there? So I can use this same equation, plug in what I know, and solve for what I don't know. So if I'm looking for the 95th percentile, then area under the curve to the left of 0.95, that would be inverse norm of your 0.95 with a 0 and a 1. This is using the standard. Standard means z-scores. So you can plug that in and get 73.29. Try that on your calculator, make sure that you get the same thing. So over here, we were able to go from a percentage, from z-scores and x bars to a percentage, which happened to be 0, or proportion, or probability. Those are all the same thing. Over here, they gave us the probability, the proportion, the area under the curve. We took that and plugged it into our calculator using inverse norm to get there. So you can use inverse norm here, your calculator, to get to this number. Up here, you can also get what we used as normal CDF. So if you need to review that from chapter 6, go back and read through the notes or through your workbook.